A few weeks ago, I knew pretty much nothing about AI, but here I am about to unveil my hand-built and hand-trained AI model to the godfather of machine learning on YouTube, Seth Bling, and ask him to rate my work on a scale from 1 to 10.
Seth, thank you for being here. Is it okay if I call you Seth, or should I call you Seth?
Yeah, no, Seth is great.
It's a neural network that I've been trying to teach to play video games better than a human can. It mimics the same principles as actual evolution to improve over time, and it has a structure that's inspired by the neuron connections in an actual human brain. But the craziest part of this project is not the simple math that at scale can create surprising levels of intelligence. It's something much more subtle that I only ever would have learned from walking this incredible path of self-study. And I will share that subtle thing with you, and we'll find out what Seth Bling thinks of the project.
I think that's like one of the biggest bottlenecks of, I guess, evolutionary training. You need a lot.
Yeah, but I need to show you this other really cool thing first. A couple weeks ago, I decided it was time to take a stab at this dream project that I've wanted to make way before I ever even learned to code. And after some initial research, I started to think that if I could just wrap my head around a handful of key principles and concepts, I might actually be able to build my own AI model. A few hours later, I found myself reading this free textbook on coding principles. And in chapter 9, I learned to build something super cool that low-key blew my mind. Say you want to create a program that guesses a simple hidden phrase that's 18 characters long. I'm gonna keep this secret from you for now as well. You could just create an infinite loop that guesses at random until all 18 characters in the string are correct, but there are 27 possible characters for every one of those 18 slots. That's 27 to the 18th power of possible strings, which is a lot. Don't worry, I'm gonna write some very inefficient programs in this video, but not that inefficient. A somewhat more efficient and a very much more interesting approach is to evolve towards the correct string over time by creating an environment that mimics natural selection in the real world. In nature, the creature best fit for their environment are the ones that survive long enough to reproduce. And when they do reproduce, their offspring inherit a mix of their parents' genes. Repeat this cycle for a few million years and throw in a bit of mutation to spice things up, and you get things like camouflage, echolocation, and whatever the hell this thing is. All of these incredible traits in nature just emerged from these three simple rules. The fittest survive, genes get passed down, and there's a small chance for mutation that keeps things a little spicy. What does this have to do with guessing a string? Well, to start, we create a population of completely random strings of length 18. Every string, or element, in the population gets measured based on the percentage of characters that are correct. Out of all of these randomly generated strings, maybe one randomly landed an E in the right spot. That 5.6% correct string gets rewarded with a higher chance to breed from my fitness function. And yes, strings can breed in this program, at least. Two parent strings make a child string, and the child string takes a random chunk of its characters from parent A and the rest from parent B. So let's make a breeding pool from our winners, generate a new population, and sprinkle in a small chance for random mutation. This is actually all we need to create the circle of life. The cool thing is that any modern computer's CPU can do this almost instantly. And if we repeat the process for hundreds and hundreds of generations, we'll slowly start to watch our message emerge from the randomness. Look at that. What a nice message. A ton of work went into this video. It would mean a lot to me if you would consider subscribing. The textbook then went on to apply the same mechanic to a population of rockets trying to reach a target. After a little bit of honest coding time, boom, the rockets evolve over time to get closer and closer to the target. The best part? You can watch the rockets slowly accumulate knowledge over dozens and dozens of generations, inching closer and closer to the only goal that they've ever had to work towards. And then, right when they're about to ascend and achieve everything they've ever wanted, you just move the target and watch their entire species lose everything. Keep this evolution system in mind, by the way. I eventually found myself using it at a much more complex scale. But anyways, I was stoked that in just a few hours, I went from knowing pretty much nothing about machine learning to making this. If things stayed this simple, I would have this whole project done in no time. I actually already had a pretty good idea that the next thing I needed to learn about was neural networks. And that's because I've had a particular project in mind ever since I was 15 years old, when one of my favorite Minecraft YouTubers took a left-hand turn in his content and uploaded this video. It was about a program he made that could actually play through an entire difficult level of Super Mario World all on its own. And not just play it, it was spin jumping, taking super tight jumps, and beating the level fast. This blew my 15-year-old world mind, and ever since I saw it, I've wanted to try to implement it for myself. So that's the project. The goal was to make a neural network and train it to beat a level in Super Mario. And the best part? The creator of the original project himself, Seth Bling, agreed to check out my project and give me some honest feedback. But I only have 3 weeks until our call, so I have to hurry up and get this thing working if I want to impress him. So naturally, I dove into learning the actual mechanics of a neural network. As a beginner programmer, I'm still very careful about how and if I use AI. I still code almost everything by hand because I'm just learning, you know? But code reviews matter more than ever before because of AI. There's more lines of code being shipped than ever before and less lines being actually read, which is why this portion of the video is being sponsored by CodeRabbit. CodeRabbit is not an AI that writes code, it's a code review agent. You open a pull request, it reads the context of your code base, and it identifies problems. And for a lot of issues, it offers you a one-click fix. CodeRabbit's new change stack actually breaks down PRs into groups of related changes, puts the most important stuff first, and gives you all sorts of helpful summaries and diagrams. It even learns and adapts to your coding style over time. So check this out. I opened a pull request on the repo for the project in this video, and it found all sorts of issues. I definitely have all sorts of blind spots, and I would not have found these myself. This is pretty sick. CodeRabbit is installed on over 3 million repos. It's used by over 100,000 open source projects, including Bun, and it's doing 2 million PR requests every single week. So if you want to catch and fix issues in your code base faster, check out CodeRabbit at coderabbit.link/commonluke. Now, let's get back to the video. Your brain is a network of roughly a whole lot of neurons. Each one is a little cell that listens to signals from its neighbors. And if it gets excited enough, it fires off a signal of its own. A single neuron doesn't know anything, but a whole brain's worth of neurons working together knows how to walk, talk, and even leave mean YouTube comments. A neural network in machine learning borrows this idea. It's made up of tons of fake neurons that are linked together, except all of our program's neurons are going to be doing math. And actually some pretty simple math at that. But at scale, neural networks are capable of learning incredible things. Time to code one from scratch. The textbook I was reading started me off by coding a single neuron. It takes some inputs and each input gets multiplied by a weight. Add up all the products and something called a bias and then run it through an activation function of your choice and boom, that's literally all the math you need to get a neuron to learn a simple pattern. This neuron looks at a random point on a graph and guesses whether it sits above or below an unknown line. Every time it guesses wrong, the weight gets nudged in the direction that would have made it less wrong. And a couple thousand guesses later, we're left with a trained neuron that knows exactly where the line is, even though it's never seen it. By the way, all those exercises were from The Nature of Code by Daniel Schiffman. It's a free textbook, and I recommend that you check it out. Now, let's find something that'll teach me how to make a neural network from scratch. How about this video series by my boy SentDex? Instead of focusing on single neurons, this series jumped straight into coding entire layers of neurons. I've been using some pretty simple terms like multiplication and addition, but what we're actually dealing with here is linear algebra. Because when every neuron in one layer connects to every neuron in the next, you can store all the weights in one big grid of numbers, a matrix, and compute an entire layer in a single matrix multiplication. So up until this point, I've learned how to make a population that evolves towards a goal and how to write a neural network by hand. But there's one more important ingredient before the magic really starts to happen. I need to find a way to write some code that can control a Mario game, which is much easier said than done. I found this Python library called Jim Super Mario Bros, which spins up a real NES emulator and lets my code create inputs for the game. I started by just testing a different random input for every frame to make sure that it was working. Then I created 10 games and ran them in tandem and gave them all their own series of random inputs. Figuring out how to render multiple games dynamically was so much harder than I thought it was going to be. But now I just need to give them all their own neural network. The great thing about this package is that all the hard RAM scraping work is already done for me. I won't need to go digging through thousands of rows of NES memory maps because I can just pull everything from this built-in game info. Oh shit. Okay, so what I'm looking for actually isn't in here. There's plenty of info about Mario, his position, his coin count, but there's really not that much about the world around him. This wouldn't be a problem if I was trying to create a program that memorizes how to complete a Mario level by guessing randomly, but if we were going that route, we wouldn't need to make a neural network at all. We could just crossbreed a series of random inputs until we beat the level, like our rocket exercise from the textbook. But I'm not trying to make Mario memorize the level. I want him to learn to play the game, to actually actually understand obstacles and enemies. This will hopefully allow him to complete multiple levels with one well-trained neural network. And that means that my boy needs to see. So it turns out we're gonna have to dig through the RAM maps after all and build out a whole system that translates what's loaded into the game's active memory into an easy to interpret grid for my Mario bot. I was able to find a somewhat similar project on GitHub that found a way to translate RAM states into a clean grid of numbers that represent tiles, enemies, and our boy Mario. So between that repo, public RAM maps, and a lot of trial and error, I slowly pieced together a way to translate the active RAM states into something digestible. And here it is. It's a big grid of numbers. Wherever there's a 1, it means that there's a solid ground or pipe or a block, and a -1 means that there's an enemy, and the 2 is Mario himself. Setting this up was actually one of the most tedious parts of the entire project, but struggling through this gave me a new appreciation for the amount of work that all the creators of all these neural network projects have had to go through to get it done. I wonder if Seth will be able to relate to the struggle when he reviews my project, but that'll have to wait. The good news is that now we can feed the environment surrounding Mario into our neural network cleanly. Since this grid that we made has 208 total numbers, I made the first layer of our neural network have 208 inputs. And we already know that the final layer of our network needs to have 12 possible outputs, since that's the amount of inputs that the GYM Super Mario Bros. Library recognizes. Finally, I added in something called a hidden layer, which basically just means that it sits somewhere between the input and the output layers. I decided to start it at 18 neurons. I had no idea if this was an appropriate number, but I just rolled with it. I would end up tweaking this a lot later on. In the simplest possible terms, this neural network takes the state of the game as an input, runs it through dozens of neurons, and out the other side comes 12 numbers, one score for each possible move. Whichever move scores the highest is the button that Mario presses that frame. Finally, we just make our whole neural network a class, create a new one with random weights for each of the 10 Mario games, plug them in, and bang. One of the coolest moments of this project for me was when I initially got the neural networks linked up to the separate games. Because even without any training, I saw my 10 Mario emulators go from spamming random inputs to spamming random behaviors. Some would run back and forth infinitely, some would jump forever, some would hold right, but most of them just did nothing. This was my first time doing any of this, and I just thought that it was so cool. Okay, now that we have game rendering and neural network design figured out, I just need to build a fitness function and a breeding function. I settled on 3 things: how far each Mario gets, a big bonus for beating the level, and extra points if they do it fast. If a particular neural network does well, it'll have more chances to breed in a breeding pool, and if it does breed, its weights will be mixed with another neural network's weights to spawn a child neural network. It's just like our string evolution, but for a much more complex system. So I spawned a population of these networks, every single weight completely random, and let them loose for a 24-hour training run. And when I came back to check on them the next day, they hadn't learned anything. Yeah, it actually took me a ton of attempts to get this right. I had to tweak the fitness function many times, change what conditions the individual emulators run under, add more neurons to the hidden layers of networks, and a whole bunch of other stuff. I spun my wheels trying to get a successful training run for like a whole week until I finally got this beautiful result. Oh, did you hear that? Our training run is finished, but I'm out of time. Seth Bling is literally calling me right now.
Seth, thank you for being here. Is it okay if I call you Seth, or should I call you Seth?
Yeah, no, Seth is great.
All right,
yeah,
cool.
I already recognize this is Super Mario Brothers 1-1, right?
He was super nice and genuinely seemed interested and just as excited about my project as I was.
This was painfully slow on my computer. Unfortunately, I didn't like kill the emulators if they died or anything.
Yeah.
It all just ran the whole time.
I think that's like one of the biggest bottlenecks of, I guess, evolutionary training. You need a lot
Yeah.
of processing. Like in real life, you have massively parallel systems in terms of we have a billion humans. Like those are all being, I mean,
Yeah.
not simulated. They're, living life, but every organism has, millions or billions instances running at the same time.
But once I was done walking them through it, it was time. Time for the Mario Gauntlet. I did all this work with one goal in mind for my Mario AI, to have it learn to play Mario. And the best way to test that is to pit it against a series of various levels from different parts of the game to see if it could complete them.
Okay, let's let it rip. Some incredibly tight movement from Mario here. Barely missing the spikies at the start.
Is this a deterministic simulation? I would think it probably is.
At this point, the neural network weights aren't changing at all, so we could run this 10 times in a row, and it's going to have the exact same result.
Okay. Oh, there we go. All right.
There we did.
Okay, now we're 1-1.
Done. And here's 1-1. This is brand new territory for it.
Look at that. This is quick, too. Yeah, this is good.
Yeah.
It's like avoiding a lot of blocks. I wonder how much of that's intentional. Uh-oh.
Yeah. Yeah, I don't think that structure appears anywhere on 4-1. All right, here's 8-2. Look at this crazy staircase.
Okay. It waits for the enemy there. That's actually...
Could be. It looks like he waits. Never seen a spring.
Wow. That is a hard section to get past, actually. Like, even just playing casually.
I think...
It's just running under the enemy.
I think it's all luck at that point. I think it's all luck.
That is impressive. We'll just call it impressive, okay?
Thank you. Yeah. But Seth, you are the godfather of Mario AIs. Obviously, we have not dove into the code in this. We've only been looking at the highlight reel of this entire project. And just based on the vibes here alone, I'm wondering if you'd be willing to rate my project out of 10.
I mean, honestly, like, it sounds like it was a 10 out of 10 project. I'm not saying that because I think this is like the greatest neural network I've ever seen. Obviously, these days we have, insane neural networks that do crazy things.
We have
I'm saying that because I think that you got to experience like the entire gamut of what it takes to make something like this. You got to like learn about neural networks, learn about activations and architectures. You told me about your architectural choices and like you're aware of other architectural choices. You learned like all the ways that they can fall down. You had to learn how to like dig into basically like reverse engineer a game, which this is something that like I've spent a ton of time doing, and all of the problems that you had, I also had, probably also when working on Mario. So like the amount of like experience you gain doing all this is just like really valuable, and it's stuff that you can apply to a lot of other very different contexts. So yeah, 10 out of 10.
Could not have put it any better myself. Yeah, the craziest part of the project was just how much freaking fun it was. Huge thank you to Seth again for participating in this video, and thank you so much for watching. See ya. Oh, the pillow has nothing to do with this. It just helps with the audio. It reduces the echo in here. See you later.